Please work. Okay, I got it going. All right, this stuff today might stretch your brain a little bit. There's a lot of thinkies in this. All right, let's get into the first one. The first one is so try to think of this stuff that we're talking about today, not like, my intent is not for it to be thought of as like a set of procedures, more of just a general way of thinking about really any equation or function that you might ever encounter. So everything in the next few problems, let's do what's it, 17 through 18. No, that's 36. There's a decent chunk of these questions. Oh, she's here. All right. Were they correct that you thought it was lunch? That's what they thought. They're like, I bet she went to lunch. Okay, I marked your present. There you go. Okay. First thing, look at this. Domain. So typically when you're looking for a domain, you ask the question, what x values aren't allowed to go into this? -2. -2, very good. So why can't -2 go in? You can't divide by 0. Right? That's the thing you can't do. There's other things you can't do. You can't square root negative numbers. You can't take, say, logarithms of negative numbers or 0. But luckily for this, you don't have to worry about that stuff. So your thinking pattern has to go towards all that's happening here is some subtraction, some addition, and some division. So really all I have to worry about is division by 0, which means that this denominator here, this bottom, can't be 0. So that means that x can't be -2. So do you have any questions on that first step there? Sure? All right, great. X can't be -2. Now that'll lead to, in a minute, what does that actually mean graphically? Like, is there just going to be like a little gap there, or what happens there? So yeah, very good. It's going to end up being vertical asymptote. So we'll talk about why that is, okay, in a second. X-intercepts. So what does it mean to be an x-intercept? So if you're an x-intercept and you are crossing on the x-axis, which means your y value is 0. So this basically is asking the question, how is it possible for y to be 0? So if it helps, you could write a little, you could, if you're having trouble keeping your thoughts straight, you could go, how does this get solved? What is the solution to this question? Well, you can apply some algebra here, but it's actually much easier to think about this. Like that's a fraction, right? What's the only way for a fraction to be equal to 0? The top is 0. That's the only way it's possible, right? So basically, this very quickly in your head can just become this. What's the answer to that question? 1. So the answer to the x-intercept question is whenever x is 1, y is 0. Are we okay with that?
Yes.
Keep in mind that the x-intercept is a point. Points have an x and a y coordinate and parentheses and stuff. So I noticed some of you guys on your problem set, you weren't putting parentheses. I know it seems kind of like a minor thing, but yeah, put parentheses. That's the point. Okay, so moving on. How about y-intercept? How do we find?
Set x to 0.
Plug in 0 for x. This one, all you got to do is plug in 0 into the function. So if we plug in 0, the y value will be -1/2. Is everyone okay with that?
Yeah.
You're cool with it. Next, the last things you see there are asymptotes and end behavior. So the vertical asymptote you're going to find is very closely tied to domain on rational functions. So let's have a quick little digression here. Long story short, the vertical asymptote is x equals -2. So if you're wondering what's the vertical asymptote, I'm dying to know. That's it. So why is that? So what's a number? So like just generally speaking, at a vertical asymptote, what happens? Something like this. Either this happens or this happens, or you get the idea. So at a vertical asymptote, as the x values get close to that asymptote, what do the y values do? They get huge. They blow up to infinity. So I just want to show you real quick. Why is that happening on this one? Well, what's a number really close to -2? I don't know. How about -1.99? That number is pretty close to -2. It's not like super close, but it's pretty close. If I plug that number in, let's look at what kind of y value we get. So plug that in there, you get -1.99 minus 1 over -1.99 plus 2. So the top would be -2.99, and the bottom would be 0.01. Does everyone understand that arithmetic there? Hopefully, yes. So, well, 2.99 divided by 100th will give you that. So that gives you hopefully some good insight into like, oh wow, you plugged in a number pretty close to -2 and got a pretty gigantic y value in response. That's exactly what a vertical asymptote is. It's this behavior on a function where as you get really close to this value, you get larger and larger y values in either the positive infinity direction or the negative infinity direction. Okay? Long story short, if you have a value that causes this to be basically a non-zero number divided by 0, so specifically here, if you plug in -2, you get -3 over 0, you'll have a vertical asymptote. Okay? In a few days, we'll go over this peculiar case where if there's a number that actually makes it 0 over 0, you get even weirder behavior. You get something called a hole. Or you typically would get a hole on a function like that. So, okay. Any questions on that? If that confused you, let me just clarify once and for all. Pretty much 99% of the time, this number is going to be a vertical asymptote. Okay. So let's look at end behavior. And then we'll come back to horizontal asymptote. So end behavior. What do we think? Okay. Don't shout it out if you know it. I want to give everybody a chance to think about this one. On this function, as the x values get bigger and bigger and bigger and bigger as they approach infinity, what do we think happens to the y values? I appreciate your willingness to answer, but I wanted to give everyone a chance to think hard about this one. Some food for thought here. If you're confused, pick a big x value. What if x was 1,000? What would the y value be awfully close to? What if x was 10,000? What would the y value be awfully, awfully close to? All right, who's got an answer? Is that confident in it? No one?
2.
Oh my goodness. Alethea?
0.
No.
-2.
Hambanan?
Infinity.
Infinity? No.
-.
Hold on. Let's simplify this. Okay, think about this. Concrete answer here. If x were 1,000, the y value would be awfully close to
1,000.
Guys, okay. All right. Let's try this again. Okay. Let's plug in 1,000. Who said 1? Yes, the answer's 1.
Come on.
May pointed out a really good real-world example of this. When you're measuring, like on an English units ruler, like 15/16 of an inch is awfully close to 1 inch, right? Or 31/32 of an inch is awfully close to 1 inch, right? Or say I give you, you get, here's a cake, but you're only going to get 999 thousandths of the cake. You're getting pretty much all the cake, right? You're going to get pretty much all of it. Does this make sense or no? Okay, so if you plugged in a big number to this, then the top and the bottom would be very close to each other, right? They'd be very similar numbers. So this would be approaching 1. Does that make sense to everyone or no?
Yes.
Same thing. What if x was negative 1,000? Same story, right? I have negative 1,001 over negative 998. Negative over negative makes positive. So you get the same end behavior. There's a trick to this, which gets into like a very important math concept of this idea of like dominant terms. So looking at the top, let's think dominant terms here. Who do you think's the dominant term between x and 1? X. Which all that means is if x is big, let's say x is $1 million. Okay, I give you $1 million, but then I take back $1. You still got $1 million pretty much, right? For all intents and purposes. Same thing on the bottom. I gave you $1 million, and I gave you $2 more. Okay, it's still pretty much $1 million. So the trick here is you just kind of ignore the non-dominant terms, and then you see, oh, okay, I've got x divided by x, right? So the ratio is 1. Thumbs up. Okay, now horizontal asymptote. There's nothing special about this. This is basically just another way of writing this information. So the way you write this is there's a y equals 1 horizontal asymptote. So really all the horizontal asymptote is a concise way of expressing the fact that this function approaches 1 in its end behavior. All right, how are we feeling, guys? All right. Poggers. Oh, thanks for the 5 gifted. Gotta make sure to keep the fans, right, Sean? Yeah, thanks for the 100 bits. Okay, let's put it all together. This is typically the hardest part. So, most likely, for most people, they find this process, putting the stuff on the graph should be easy, but then getting the actual curve to fit is typically the hardest part, so don't feel bad if you're confused by that part. But you should hopefully understand each individual thing. If you don't, please just talk to me individually or do something, take some action to make sure you understand each individual piece of where they're coming from. So domain and vertical asymptote, maybe put that first. The order doesn't really matter. You're just going to put all this on the graph. So how do I draw a vertical asymptote? You just do this. Dashed line. This equals -2. There's my vertical asymptote. That's not really part of the function, but it's sort of a framework that the function is kind of constrained against. Horizontal asymptote of y equals 1. So I think did the printer make the little tick marks noticeable?
A little bit.
So sorry. But you can just put your own. Okay, now let's put on there. We have some points. That's always nice. The more points you know, the typically the easier it is to fit it on. We have 1, 0, and we have 0, -1/2. That's all we have. So that's all we have to work with. But now, do you see, now the key here now, getting it all together, is to really understand what is an asymptote. An asymptote is this thing, is a flat line or vertical line that your function is going to approach in the long run. So what's going to have to happen over here? Has to approach it. As I approach this vertical asymptote, I have to approach the line. So what you're going to have here, the ruckus. The ruckus. There we go. That's one of them. Yep.
How does that line have the end behavior x to -infinity, y to 1?
Because we're not done yet.
Oh, okay.
It's a great question,
That
though.
would solve it.
You could certainly, I actually thought about asking the students to like talk about this behavior, but I didn't want, a lot of times end behavior is already overwhelming enough for some people, but you certainly could make statements like, as x approaches -2 from the right, the function approaches -infinity. So you can make a whole bunch of different statements about the behavior of the function at certain x values, and that's basically this idea of what they call limits. But yeah, this is a question that people ask all the time. So if you're feeling this question of why is there stuff over here? So spoiler alert, we're only halfway done. There's a curve over here. There has to be, because we established that any x value other than -2 has to be valid, right? Well, there's a whole bunch of x values over here that are not -2. So for example, -3, -3.5, -1,000,000. Like there's a whole bunch over here. So those have to have points on the graph, right? Does that make sense? Okay, so question is, does it do this? Or does it do this?
That.
The answer is this. Now, why can't it do this? There's a bunch of reasons. I'll mention a couple of them. One reason why it can't do this, because when you're thinking about these, you want to be flexible in your thinking and think about how can I rule out certain things that aren't possible. So like, if I wanted to do this, I would have to pass through the x-axis, right? But that's a logical impossibility because I've already listed out all the x-intercepts. So there can't be another x-intercept. Doesn't make sense. Another way is, do you see how all these points have positive y values? Well, I can confirm that by let me think of a negative number that's over here, like maybe -5. If I plug in -5 into this function, I'd have a negative number on top and a negative number on bottom, which makes a positive number. So that would confirm for me that for any, and you can actually reason out on this, that any number to the left of -2, if you plug it in here, would produce a positive y value. And so that would help you understand why you're constrained to that space. All right. Do you guys feel okay about this stuff?
Yeah.
Let's do one more together, and then we'll have some time to some work time. Let's do the next problem. The next problem's a little bit more, tends to be slightly more confusing. Hopefully not ridiculously so. Okay. Does anyone have just an initial thought the second you see something that looks like this? Very good, very good. Anytime you see an expression like that, you're hopefully going, oh, let's see if I can factor it. Because often if you factor it, you get extra information. So let's start by doing that. A little bit of factoring review for you. So we ask, what two numbers, first we say yes, because this number is a 1, which makes it easier. What two numbers add up to be 1, and then multiply to be -2. By the way, I should point this out. I've had students before that they think about it in that order. Maybe we should say it the other way. What two numbers multiply to be -2, but add up to be 1? Because a lot of people, they start with thinking of this huge list of numbers that add up to be 1. But their list is huge. They're starting off with an enormous list to search through. No, start with numbers that multiply to be -2. Okay, well, it's got to be 1 and -2. It's the only one choice. And so +2. I think I said that wrong. It's got to either be 2 and -1 or -2 and +1. Only two things to consider. So if you're having trouble with the factoring part of this, yeah, start by thinking of what pairs of numbers multiply to be this. Alrighty, so domain. X cannot be, what do we think? 1, and X cannot be Negative 2, very good. And there's two forbidden values. Now those are going to very quickly, or directly I should say, translate into vertical asymptotes. Right? So there's going to be a vertical asymptote of x equals negative 2. And a vertical asymptote of x equals 1. If you'd like, you can confirm for yourself that, say, what's a number really close to 1? I don't know, 0.99. If you plug 0.99 into this, you're going to find that it produces a very large y value. In fact, the closer you are to 1, if you plug in 0.9999999 into this, you'll get a really big y value. So the closer you are to 1, the bigger the y value produced. Same thing with negative 2. Okay, x-intercepts.
0.
Very good, 3, I think. I asked the question, how can I make the top of this fraction be equal to 0? This often throws people off because it's a trivial answer. You go, how do I make that 0? Oh, just pick 0, and you're done. So if x is 0, it makes the whole thing 0. But wait a second. That's exactly what a y-intercept is. So the origin is an x-intercept and a y-intercept. Horizontal asymptote time. Okay, now this one might confuse you. Here's another one. Go into the deep think tank. Looking at this, we can go. What makes this one more confusing is now it's like if x is big, let's say x is 1,000. Well, the top's 1,000, and the bottom is going to be awfully close to what number? If x is 1,000. Not 1,000, because this first thing squares it. What's 1,000 squared? A million.
1 million.
Yeah, so now think about this. If you want to get the exact number, it's 1,000,000 plus 1,000 minus 2. But back to that like money thing. If you get $1 million, $1,000 is like, who cares? I got $1 million. So the same idea of dominance. Okay, this is the dominant term. So I ignore these guys, and I say if I had a really big number. By the way, what is 1,000 divided by 1 million is awfully close to what?
1,000.
0. I'm sorry, I didn't hear it.
Wait.
Let's say I had $1,000 and I wanted to split it up amongst 1 million people.
Oh, I got that backwards.
Each person's gonna get 1/10 of a penny. Right?
Yeah.
Makes sense?
Yeah.
Get a lot of blank stares here.
I thought you said 1 million divided by 1,000, and I was like,
Ooh, that would be good. Yeah, if you're one of 1,000 people and there's $1 million split between you, you just get $1,000. That's pretty good. But no, so do you see how the bigger, long term though, the bottom of the fraction is going to be much bigger than the top of the fraction. We sure we understand that?
Yes.
One extra trick you can use for end behavior, because this tends to be one of the thing that people get hung up on the most is the end behavior part of things. If I cover up the non-dominant terms, do you see how I have x over x squared? So for my end behavior, I can say, well, x over x squared is like 1 over x, right? So my function is going to have the same end behavior as a 1 over x function. And luckily, I've studied that function before, so I already know, I have a pretty good sense. And this also gives you extra information. It tells you that not only is it going to approach 0, but it's going to approach 0 from the top and then from the bottom on the left. So that's extra information that's helpful in understanding the function. So this is a very good technique to make sure you understand. But so I got to write the end behavior in the correct notation. So as x approaches infinity, y approaches. Hopefully we know the answer by now. 0. As x approaches negative infinity, y also approaches 0. Same idea. So my horizontal asymptote. You can see why the word horizontal asymptote is a thing, because it's much more concise to say this than to say all that. Right? It's a very concise way of saying a kind of a large amount of information. So,
I'm noticing a pattern.
and
The horizontal asymptote is the same x value for the x-intercept. Well, it was for the first one we did too. So the first one we did, the horizontal asymptote was y equals 1, and the x-intercept was 1, 0. Is that not a good? No.
what do we think? Is that just a coincidence?
No, nothing's a coincidence in that.
Well,
That's what-
here's the thing. So it's good you're looking for connections there, but well, let's say this number was at 3 instead, Julia. So like, let's say that was a 3. If I just change that one number to a 3, then now my x-intercept is 3. But would that have any effect on the end behavior?
No.
So it's certainly a good thing to. Someone in the other class had a similar like comment about like how there was a 1 there and a 1 there, but ones do pop up a lot in mathematics. One is like a very ones and zeros come up a lot, and yeah, thanks for bringing that up. That's a great point. No, it's good. It's good to say. Good to mention. So the connections that definitely are there though are the domain and vertical asymptote, strong connection. The horizontal asymptote and the end behavior. I mean, I wouldn't even say it's a connection necessarily. They're literally the same thing. They're just different ways of writing the same fact. So there you go. All right, ready for the difficult part?
No.
Thanks for that idea. I appreciate it. Okay, so let's put the information on. Let's get maybe the vertical asymptotes in first. We're gonna put the dash marks in first. There's dash marks.
No scribbles.
Okay, so there's a vertical asymptote of x equals -2. Here's a vertical asymptote of x equals 1. Horizontal asymptote of y equals 0. That's just the x-axis. Unfortunately, we only know one point that lives in the graph, so that's, I mean, obviously the more points you know, the easier it is to fit a curve onto those points, but okay, so we gotta make this work. So let's start, you can start wherever you want really, but I a lot of times like to start on the right side. So can there be any funny business of like, can I cross the x-axis?
Never.
Why not?
Because it's a horizontal asymptote.
You can cross a horizontal asymptote. That's correct though. We've already listed all the x-intercepts. There's only one. If it crossed the x-axis over here, we would have already listed that point. So it can't cross here. So either it's going to be, well, let me ask you this. Does it make sense how it either has to be zoop or zoop? There's only two options. I've seen people draw in very weird shapes before. I mean, I've seen people draw in things like this. It doesn't make you like a bad person, but you are severely confused if you're thinking about this. You need to try to address your confusion because that's not even a function. Okay? So hopefully our understanding is, what I'm trying to say here, guys, is this last step is challenging. It's a challenging step, but as long as you understand what an asymptote is, you understand that I have to approach the vertical one and approach the horizontal one. So either I have to do this or this. So the answer, it turns out, is this. Two ways I could have figured that out. Well, there's at least two ways. How about this? What we talked about earlier. I've established already that this guy has the same end behavior as this famous parent function. And this famous parent function approaches 0 from above. So therefore, this guy must. Or I could have just plugged in a number like, let's say I plug in 3. If I plug in 3, I get positive number, positive number, positive number. You see what I'm talking about? You'd have a positive number divided by the product of a positive and a positive, so that's positive. And it stands to reason that any number I pick that's bigger than 1 would produce a positive y value. So every number over in this world over here has a positive y value. Let's get the left side. Well, I've already established the end behavior. Again, I can plug in a number that's less than -2 in here and confirm that, let's say I plug in -5. Negative, negative, negative makes a negative. So that means I'm constrained to live down here. All right, this is the hardest part. What's it gonna do? This is where you can get into some very interesting ideas. Do you think it's gonna bounce off the x-axis? Could it possibly come down and like bounce off?
It's the only choice.
The answer is no, it can't bounce off because the term that generated the zero, what thing up here generated that zero? This guy did. If that guy had been like x squared, then yeah, we'd have a bounce. So it connects back to that polynomial thing of like what's creating these zeros. Well, this guy would just create a passing through zero. And there's even more stuff you can think about, which is who generated this asymptote? This guy. Well, think about what 1 over x minus 1 looks like. What kind of asymptote is that? Is that an asymptote that does this? Or is it one that does this?
I like that.
It's the latter. So that makes sense what I'm talking about? So what I'm saying is if I just had 1 over x minus 1 by itself, the type of asymptote that he generates is a going in opposite directions asymptote. And so it's exactly the kind of asymptote we're going to find here. So if we put all that stuff together, long story short, it looks like this. Notice it's doing what it has to do. It has to approach this asymptote, has to approach this asymptote, and has to pass through 0, 0. That last part, I assume you'd agree with me that the last one's probably the trickiest thing to reason out, given what we've covered. So, all right. Well, thanks for your attention. That's all I got for you for today. And this recording. A bad